Hi, good morning. It's good to see you all today. I got a good morning from Asa Varaj and Lord Melbury. Good morning to you. How's the weather where you are? Today, here, it's sunny. Yesterday it was a bit cloudy. Today it's sunny. Nice, relatively cool weather, but they say by the end of the week, it's going to be up in the lower 90s. Let's see, what is that in Celsius? I don't know what that is. I'm sorry. I can figure this out. So the low 30s. So kind of, it seems like a little bit early for getting up into that kind of weather this year, but it has been a strange year weather-wise. Let's see, December we had a whole bunch of rain, probably about 2 to 3 times the normal amount for that month. And then it's just been completely dry since then. Like we've had maybe 1 day of a trace amount of rain since then. So it's kind of sad. That means that even though we had a really great December, we're actually below average for the year. Good morning, Mary. Good to see you here. Sorry, just getting things set up. Oh, in India, it's already 35 degrees. So 35 would be about almost 100 for us. Yeah, 90, to us Americans, 95 degrees. So that's what we would expect to be the weather like in July here. Upper 90s, low hundreds. That's true in India, at least probably where you are, it's summer, or it's probably what, fall now, right? So it's just a little bit beyond summer. All right, so before we dive into today's content, is anybody having trouble with the current programs and needs a little help on it?
Yeah, I did see your email today.
Good.
This morning. Is that what you talked about, like doing it in this session?
Yeah.
Okay, yeah, that's fine.
You want to do that?
Yeah.
Okay.
Log into my VIA real quick.
You know what we can do is I can actually log into yours.
Oh, really? Okay.
Yeah. It won't be quite the same experience, but at least we'll be able to look at the files. Let's take a look here. That's something that we need to work on, is we, meaning mine and me and my students who are working on this, is some way to actually launch Thea so it looks just like it does for you,
yeah,
rather than going into the command like I'm doing right now. Okay, let's take a look. So in the front window here is your volume with your files. And which one are we looking at?
Hold on, where are we? Oh, okay, I see. Okay. Crack 2, it's in the Crack 2 directory. And then I believe it was the crack.c.
Okay, so this one right here.
Yeah.
Okay. Let's go ahead and Can we go ahead and just run it? And
Yeah, it's gonna be completely different because I'm in the middle of like testing it out. Yeah.
okay. So is
um,
this expected behavior so far?
yeah. So basically, what's going on is that it's not scanning through, it's not matching the passwords with the hashes, even though those are the hash codes in for the passwords. Like I've
Mm-hmm.
checked it. I want to encrypt the um So, but the thing is that there's a space in between. So I'm like, did I like not remove the null or the new line character? But like I did, and I don't know. So,
So that's actually the first thing that jumped out at me is this double spaced.
mm-hmm.
And if that's not what you expect, so maybe you wrote the program so that there shouldn't be a double spacing, but it's coming out double spaced. That's actually a really subtle but important clue
Yeah.
that
So because it,
something's not quite right.
yeah,
So now let's go and look at your program. Okay, so we've got your main here, and then we open the file for reading.
yeah, and then
Mm-hmm.
that was the length of the hash. Cycle through it line by line.
Uh-huh.
Remove the new line character, replace it with the null. And I put a print F below that
Mm-hmm.
because I was like, I just wanted to make sure that I'm actually getting the right hashes.
Mm-hmm.
And then I called my crack hash function, which is above that. But
So I think the thing to do here would be, let's not worry about the crack hash right now, right?
okay.
Because that double space thing is, like I said, I think maybe an important clue as to what's going on. So I ran make test, and you can see that it recompiled your program.
Okay.
So still
I want to
coming
make
out double
sure, like,
spaced.
am I doing something wrong in the make file?
No, I don't think so. That makefile looked okay. So the problem, if it is what I think it is, the problem is actually somewhere around here, because this is basically your whole program right now, right? These lines that I've highlighted here, these 8 or so lines, this is basically your entire program. And the double spacing is happening in the body of the while. So let's just take a quick look and make sure that everything else above that looks okay. So the first thing I see is, is the file actually getting opened? And I think we can probably agree that yes, the file is getting opened because we are seeing something on the screen. Is it reading lines out of the file with this statement here? And I think the answer there would be yes, it is, because obviously we're seeing stuff on the screen. And then inside the body of the function, or of the loop, you have these 2 lines here, which are intended to remove that new line character, and that's the correct thing you should be doing. But then you print it out. You print out the string followed by a new line, and then you print out hash line, and it's coming out double spaced.
Yeah.
So what could be the cause of that? I mean, let's just, like, without necessarily digging into the code, let's just think, what could cause that double spacing behavior? Now, I think you already hit on one of them, which was that would happen. Like I said, don't look at the code right now. Let's just think, what would cause that double spacing behavior? And we've seen that before in the programs we've written where we don't remove the new line.
Well, it got another line because I printed it out with another new line character, right?
Yeah. Let me back up and maybe rephrase what I said. In the past, when we've used fgetS to read input either from the keyboard or from a file, if we don't do anything to the line, if we just simply read it in and then print it out, and put the new line character on the end of the printf like we have, then it ends up being double spaced because there's already a new line character in the line itself, and then there's the new line character that we printed out in the printf. And so that causes that double spacing behavior. So with that in mind, you do have the code in there. You do have the 2 lines for removing the new line character. So something's going wrong there. It's either not finding the line character, or it's not removing it if it does find it, or something else is happening. So that's where we are right now, is we've got kind of like some working hypotheses as to what might be going. And this is an important step in problem solving and debugging, I think, is to make a prediction about what you think is going on, even if you don't exactly know what's going on, but what you think might be going on, and then you explore that thought and find out whether or not that's the case. So to me, we've got one of 3 things going on. We've either got it's not finding the new line character, and therefore not removing it, or it does find it, but it doesn't remove it for some reason. And by remove, I mean overwrite it with a null character. Or the third one is still this unknown, something else is going on. Does that make sense?
Yeah.
So let's see if we can explore those first 2 things where we kind of have an idea what might be happening. So is it finding the new line character? So let's look at this line here. Is this the correct way to call this function and have it search for the new line? And now I'm asking you, do you think that's correct?
Yeah.
Yeah, and I think that's correct too, because we've written several programs to use this technique. And if you're following the recipe, this is what you come up with.
Yeah.
All right. And so let's also look at this one. Is this the correct way to replace that new line character with a null?
Yes.
Yes.
Because, yeah.
So maybe it's so we still haven't determined whether or not it's actually found the new line character, or whether it has replaced it with a null character, but at least we've looked at the code and said, okay, this looks correct. So why don't we do this? Let's explore this a bit, and let's maybe, before we, let's see, what can we do? Before we go and try to replace the new line, what if we print out what hash line is before we attempt to change it?
Yeah. Okay.
Now, in order to distinguish between before removing the new line and after removing the new line, let's put some little text in there just to let us know which is which, because otherwise they'll just look the same. Okay. So before remove, %s. Oops. Oh, there's something going on here. Does anything here look suspicious?
The second before remove is below the code. Like there's a new line, right? Or
Yeah, so what would we expect this program to display? Let me go and make one more change. And I think, in full disclosure here, I actually know what's going on. So I'm kind of walking through the process of trying to figure out what's going on here. So what we would expect to see in this program is one line that says before remove and then the hash, and then one line that says after remove and then the hash, because that's what we're printing out. Right?
yeah.
Right? So we're saying before remove and then the hash, and then after and then the hash. But what we actually see is something different. We do see before remove and then the hash, and then we see after and then the hash, but then we see a before remove and nothing, and then an after remove and then nothing.
Sorry if you hear that noise. It's my dishwasher.
The nice thing about Zoom is it filters all that stuff out.
Okay.
Can't hear that. So that's strange, isn't it?
Yeah.
That we've got some lines that contain what we expect, and we've got these other lines that have just these blanks.
It's really weird.
So it's almost like it's reading in, or it's. I mean, like what could we say to explain this? And notice also when we say before remove, and then we see the hash, we don't see the double spacing effect.
Yeah.
And the after, we don't see the double spacing effect, even though that's what we observed before.
Jeez.
Yeah, so
Can we look?
this is a subtle problem here. You probably want the answer now, right?
Yeah.
Look, just give me the answer. Okay. So the answer is each line of the file in the hashes file contains a hash and a new line character, right? And you're telling fgetS here to read that line in and put it into an array that's hash length long. And what is that value? That value is 33.
Mm-hmm.
So when you read a line in from the file, there's 32 characters for the hash, plus the new line character, which makes it 33, plus the null, which makes it 34.
Oh, so it. Wait. Okay.
Okay?
So, yeah.
So
Okay.
this array for hash line is not long enough. It's one character too short.
Wait, can you show the screen again?
Oh, sorry. So this hash length here, which is 33, is not long enough. It needs to be 34, at least. Okay, because each line in the file contains 32 characters for the hash, a new line, and then the string needs to be terminated with a null. So a total of 34 characters. But we're telling fgetS that the string is only 33 characters long. And so what happens is it reads in the 32 characters for the hash, and then it knows it needs to put the null at the end, so that makes up the 33rd character.
Okay.
Okay, so it reads in one line that contains just the hash, and then the null character at the end. And then it processes that, and then it reads in the next line, which is just the new line character, the one that was left over that it hadn't read yet.
Oh,
And that accounts for that extra blank line.
I see.
So the fix here is to make this at least hash length plus 1. Or you could make it, bigger still.
Okay.
So whenever you use
Subtle
fgetS, always
differences.
make sure that you pass it in a string or an array that's bigger than what you need.
Okay.
Or at least as big as what you need. And right, this is a really subtle problem here.
Okay.
So now,
There we go.
this looks better. We don't have an extra set of befores and afters like we did before. And it says before remove, and then we got the extra space, which is kind of like what we'd expect, right? And then after, and we don't have the extra space. So that's probably pretty good. Now let's put this back in.
And the
Oh, I
the
did.
hash codes are different
Yeah, every time I run
because
make
you remove
tests,
the.
it regenerates the hashes.
So I should probably do that with the pass length then, or no? Because pass length, that's enough. That's enough.
Yeah.
No.
No password is going to be longer than 20.
So I know it was supposed to be return a character, but I just made it void just so I can see testing my program, making sure it's working. Geez, I haven't. I've been working on this for like the past 4 hours yesterday, so I kind of I woke up this morning and I kind of forgot where I'm at. So
So now we're on to why doesn't the program actually crack the hashes?
yeah. Um, yeah, so it doesn't even like it's still not matching because it's not printing out the password.
Mm-hmm. So here again would be some places where you could start
Yeah.
hypothesizing what might go wrong and maybe putting in some print statements just to see what's happening. Like, here I would just confirm for myself, is it actually receiving the target hash?
Yeah.
Dude, that looks good. I mean, so every time
It's
we call it, we do get a hash. There's no extra new lines on there. And then you open the file, you read in every line, you look for the new line character, you hash it. Ah, here's the problem right here. So this is the length of the overall array of characters, not the length of the actual string itself. The value of this is 20. But if the password
uh,
you read in was zebra, then the real length is 5.
oh, okay. So
So
then
you're
that should
passing
be
it like a 5-character password, but you're telling it it's actually 20. And so it hashes
okay.
20 bytes. So what should this be?
String length of the password.
Uh-huh. Look at that.
So it's got one.
Got one. Yeah. But you see, in your program, you said as soon as you find it, you exit.
Oh yeah, okay. So I just need to change that.
Yeah. All right, I'll leave it there.
Thank you so much. Just wow.
But this is one of those things where, you spend 4 hours on it and you're beating your head against the wall, and then finally there's a breakthrough and you figured out what was going on, or somebody told you. But it's one of those things where, maybe now that'll be something that sticks in your mind, and that'll be the first thing you look for
Yeah,
next
no,
time.
it definitely helps. I need to work on like placing like print statements here and there so I
Mm-hmm.
can see better like okay, what's working and when does it not work.
Yeah, they call that debugging with print. Just lots of print statements so you can see what's going on in your program. And you can do, sometimes you do that and now your program's producing tons of output, right? And you have to sift through
And
that
yeah, and then it's
visually.
more confusing.
I've done techniques where it's basically kind of like a binary search. Like, I don't know where in the program it's failing, so I'll find like a point maybe roughly halfway through the program, and I'll put something like, printf got here, right?
Yeah.
And then at least if I see that thing print out, then I know it got that far, and I haven't seen the problem yet. So I know the problem must be below that line,
Yeah.
right? It's not above it because I haven't seen the problem yet. So then I'll move that, maybe like, to, here, right? And does the problem exist
Mhm.
above that line, or does it exist below that line? So you're kind of like winnowing down where in the program the problem actually is.
Yeah. Okay.
Okay, so I think you're well on your way now.
Thank you.
You're
That
welcome.
really helps. I was like, I wouldn't have guessed like the first part, like maybe like a couple days later I would have saw it, but like that was not something that came across my
And
mind.
I've done this enough where I know what 90% of the common problems are. And
Yeah.
so I look at the problem and go, oh, I see it, right? I see it right away. But occasionally someone comes to me with a really strange one, just a totally bizarre one. And, I'm as flabbergasted as anyone else. But as soon as I
Yeah.
figure it out, then I store that away in my brain and go, okay, that's another thing for me to look at next time. One time someone came with me, it's like, I can't figure out what's going on. And there was a semicolon sitting over here.
Oh.
What does that do? Well, it basically makes this while loop not have a body. So
Because I mean,
this while
I get
loop
that
just
error
runs and doesn't do
sometimes.
anything. But visually, you don't necessarily see that semicolon, right? You see the braces here, you see the statements inside, and you go, what's going on? Why isn't it doing anything?
Yeah.
And then finally sending a semicolon over there. And worse yet is like if they have a huge long condition here, so the semicolon is actually like way off the screen. You can never see it.
Yeah. So when you edit this, does this reflect in my
Yeah, this is live.
Okay.
Yeah. This is the way it actually looks right now. In fact, if you had your environment up, and every time I hit save, you probably would have seen your file changing.
Oh, really? That's cool.
All right, great. Glad we
Awesome.
got that taken
Thank
care of.
you.
You're welcome. Now, you probably just solved the problem for 10 other people.
Yeah.
Because I assure you, there was at least a few other people who were going, I had that exact same problem. I had no idea what was going on.
Yeah, I hope so. Jeez, it'd be so relieving to like look at the lecture and be like, oh my gosh.
But I am really happy to see that you got started on the program and you ran into the problem, and
Yeah.
and then we're able to use this time to go through that and figure out what that is. And normally, like I mentioned in my email, that if we had 3 or 4 or 5 people here, we would all be like looking at the code and we would be like debugging each other's code. And I think there's a
Yeah.
lot of benefit to having multiple people look at it, because everyone now is learning. Everyone's learning
Yeah,
about the
for sure.
process of debugging, which I think is so important. Just that thought process of, what do I think is happening? And then let's dive into that and explore that thought, and then either prove or disprove it.
Yeah.
And then if you disprove it, come up with another thought. Okay, what else could be going wrong? And I've had a lot of students say just looking at other people's code and realizing other people have the same problems I do, right?
Yeah. Yeah.
And it's not just me. Sometimes it's really, like you said, it's just the something you overlooked, right? A stray brace somewhere, or a semicolon that shouldn't be there. And
Yeah.
really subtle problems, and you suddenly realize I'm not the only one that does those
Yeah.
things. And even I do them to this day. So it's something that you get better at with experience, but by no means does it ever just go away completely.
Yeah, it's definitely something like, because programming is very like, you have to problem solve. And it is something I know I need to work on, like my brain, like I need to train it like that,
Mm-hmm.
because it's not something that I'm like used to doing. Or like with Java, I had a debugger, so I would just go through that and find it. But like with this, I don't really have it, so it's just you have to exercise your brain more.
Yeah,
So I need to work on that.
absolutely. And it's something that you just need to do over and over again.
Yeah.
There's no magic like book you can read or website you can look at that just bestows upon you problem solving and debugging skills. There are
Like
ones
I
that
wish.
can there are ones that can help. There are ones that can help with here are some things you can try. Here are some things to look out for. Like when you see this behavior, you might want to look at this.
Yeah.
But really the only way to just get this skill is just to do it over and over again, in my opinion. I mean, like I said, there are books you can get to help you out, but they aren't just like read this book and suddenly you'll know it.
Yeah. I
It
wish it was like the Matrix, where they download Taekwondo and Keanu's brain.
that would be awesome, right?
Yeah.
You know, but then it's like, now what do you do with that, right? if you could just download the knowledge of how to debug your programs, then why are you writing programs in the first place?
Yeah.
Well, let's move on. So what we wanted to do today was learn how to load a large file into memory. Previously, when we've had a large file, we just dealt with it one line at a time. Read in one line, do something to that line, and then move on to the next one. But when we want to be able to crack a whole bunch of passwords, actually, if you've written this program already, you've got it working, you can try it out with the the RockU 100 file and the 1000 to 2000, but there's that RockU 1 million file sitting there just beckoning you to try it out. And if you run the program, you'll see that it takes like maybe 2 to 5 seconds to crack each hash. And the reason for that is that every time you have a hash that you want to crack, you got to open that dictionary file, start scanning through it from top to bottom. Sometimes you find the word that you're looking for early on, and sometimes it's towards the end. So sometimes it takes a relatively short amount of time to crack that password, and sometimes it takes a longer time to crack it. But regardless, it takes at least a couple of seconds to do each one. So if you've got 100 hashes, you could be sitting there waiting for a minute or two for it to finish. And there's got to be a better way. So one of the things we could do is, instead of opening that dictionary file and scanning through it every single time, because reading and writing to a disk file takes a long amount of time as to compared to just accessing memory. So one of the things we could do is read that file into memory and store it in memory, so we don't have to keep opening and closing the file. That will save some time right there. So that's what we're going to focus on today, is reading that file into memory so that we don't have to keep opening and closing the file every single time we want to crack a password. And then over the next few days, next few sessions, we'll explore other ways that we could improve the way that we're storing the data so that we can search it faster and faster. So today what we're focusing on is just getting that file into memory so that it is there to be accessed as fast as possible. So a file, as I've mentioned a couple weeks ago, is really just, you can think of it as being kind of like an array of bytes. And if I have a file that, at least visually to us, looks like, oh, I know I've asked this before, but like a bunch of foods or something like that, right? So we have pizza, and we have sushi. I haven't had that in a while. And what else do we have? Ice cream. Yeah, that's a food. I'll go with that. My kids think it's a food, so. And burrito. This is what us Americans eat, right? It's boring food. I always like to hear about what other people eat. Curry. Anyway, so we've got what looks to us like 5 or 6 entries in this file, but really in the file itself, they're not organized by line. They're just organized by character. So in the file, it looks like this. Pizza, and then a new line character, and then sushi and a new line character, and then ice cream, and a new line character, and a burrito, curry, and then a new line character, and then that's the end of the file. So that's what it actually looks like in the file itself. And so we could just take that file, and instead of reading it in one line at a time, we could basically just pull that entire file into memory, into one giant array. So that's the first thing we're going to do. So rather than reading the file in one line at a time, we're just going to pull all the contents of the file into memory all at once, and just read it in as one giant string that starts with the first character and goes all the way through to the end character and has those new lines embedded in it. So let's write that program first. Now, what we're going to need to do is, now we're going to have a combination of memory management, because we don't know ahead of time. We don't know when we write the program how big that file is. And we're also going to use some of the other file input-output functions. We know about fgetS for reading in a string, one line at a time. We know about like fscanf for reading in a word at a time or reading in numbers. But here, we're going to be reading in a big chunk of data all at once. We're not reading in a line at a time. We're not reading it in a word at a time. We're just reading the whole thing at once. And so we're going to use the fread function for that, to read in just a whole bunch of data. Let's call this, I don't know, load file. Let's see. Let's have it pass in the name of the file we want to read in on the command line. Which means we need to write our main using argc and argv so that we can get access to that. So the name of the file will be in argv1. Let's check first to make sure that we've got enough command line arguments so that the program doesn't crash if the person doesn't type in a name of a file. So if argc is less than 2, which means that only the name of the program was given, then we'll print out a message, usage, %s, and then file to load. Oh, this goes to standard error over here, and then we're going to put argv0 on the end, and then exit. Okay, so when we get to this point in the program, we now know that they've typed in a file name, and we're now going to open that file for reading. But before we do, before we're going to open it for reading, what we want to do is find out how big that file is. Okay, so what we're going to do is we're going to find out how big the file is, and then we're going to set aside that amount of memory, and then just load that entire file into that memory. How do we figure out how big the file is? Well, you know that if you do something like, the ls command, if you've used the command line before, the ls command will list the contents of the file, and you get information like the permissions on the file, who owns it, it's these two over here. You've got the size, you've got the date, the time the file was last modified, and you've got the file name itself. So this column here contains the size. How does ls contain or obtain that information? So there's a built-in function called stat, which I guess stands for status. You can get the status of a file, and what it'll give back to you is basically this information. It'll give you the permissions, who owns it, the size, the date, the file name, and so forth. So let's look up the stat command. So the stat function is used to return information about a file. You give it what's called a buffer. You give it a place to store that information, and then it'll fill in all of those fields for you. So what you do here is you call stat, you give it the name of the file that you want to get the status of, and then you also pass in this thing called a struct stat. Let's take a look at that. So here's what a stat structure looks like. Now, I haven't really talked about structs before, but a struct is a way in C to combine two or more pieces of information under one kind of like into one box. So, an array is a way of storing two or more pieces of information, but all the information has to be the same, like has to be an array of integers, has to be an array of characters. But a structure allows you to construct, to use that, to make a pun there, it allows you to construct a box that can contain more than one piece of information, and those pieces of information can be different things. So in this stat structure, we've got things like what device is holding this file, the inode number, which is basically a unique ID for every single file. We've got mode, which is the permissions, the number of links, the user and group that owns the file, and then down here is size. This tells us the size of the file. So we're going to use this stat function to get information about the file and then pull out the size. Let me show you how that's done. So I'm going to go struct stat, let's call it st. So the name of the variable is st and its type is struct stat. It's actually a two-word type. This is one of the few places in C where you're going to find variable types that have two words in them. So the entire type is called struct stat. Then we're going to say stat argv1, that contains the file name that we're getting information about. And then we're going to pass in a pointer to that struct that we just allocated. The stat function is going to load this file in and then fill in the fields of that structure with the information about the file. And then let's just print out I think this is going to be a long decimal number. So here's the name of the variable, st, and this is the name of the field within that structure that contains the size. So just to correlate that with what we saw over here, here's the field called st_size, which contains the size of the file in bytes. So we're just going to print that out. So I think it's about time to compile this program. Oh, let's see. We need to include standard library, and according to the manual for this, we need to also include sysstat.h. So there's a couple of includes we have to do. There we go. So I'm going to type in the name of the program and then a file name that I want to get the size of. Let's do let's do greetme.c. And it says that that file is 544 bytes long. And let's just make sure that's correct. So here's the greetme file, and it is 544 bytes long. Let's do this one here, this figlet-225.tar.gz. We should get 233,201 from that. And we do. So the stat function can be used to find out how big a file is. So now what we're going to do is just ask the operating system, give me a giant chunk of memory that is that number of bytes long, and then we're going to fill it with the contents of the file. So what function do we use to ask the operating system for a chunk of memory? While you're answering that question. Malloc. Good, good, good. So I need a variable name. Let's call this contents. It's the contents of the file. So we'll ask the operating system, do a memory allocation. This is the number of bytes I want, and then it'll pass back a pointer to the start of that chunk of memory. There was a question, can we think of a struct as objects in another language? Yes. So a struct is actually very similar to an object or a class, if you will, in other languages. In fact, early C++ compilers this is kind of a little tangent here. Early C++ compilers, all they would do is take your program that had things like class and public and private in it, and then they would just translate it into C by turning those classes into structs. And then it would just hand it off to the C compiler at that point. So the very first C++ compilers, at least the ones that I had experience with, there was one called CFront. It was a front end to the C compiler. You would pass in your C++ program, and then CFront would translate it, basically recompile your program into an equivalent C program, and then hand that off to the C compiler that already existed. It wasn't until later that we had native C++ compilers that just went straight from C++ code directly into the executable like they do now. So when you allocate this memory with malloc, it goes onto the heap, not onto the stack. So this chunk of memory is going to exist for as long as the program is running or until we free it up at the end. Okay, so we're going to use malloc. We're going to be passed back a pointer to the contents. And now we're going to fill it up. So we're going to have to open the file for reading. File pointer, let's call this F. And then let's make sure that we actually were able to open it. So if F is a null, we're going to print out an error message. And then exit. So now that we got the file open, we're going to use fread to just pull the whole contents of the file in. So we're going to call fread, and then I think we pass in 4 parameters, and I always forget the order of the parameters, so let's go and look that up. All right, so it says here fread, you pass it the pointer to where the data is going to go. So that's the first thing. The second thing is the size and the number of members. So these two numbers that you pass in contain information about how big is each basically unit of data within the file and how many of them are there. We're going to be passing in 1 for the size, and then the length of the file for the number of members. Why would you ever pass in anything other than 1 for the size? This is just kind of an aside here. You can actually make files that have a structure to them. Maybe you can make it a file of database entries where you know that every database entry is going to say take up exactly 100 bytes. So in that case, you would pass in 100 for the size, and then a number correspond to how many records there were in the database. So if there were 1,000 entries in the database, each one was 100 bytes long, then you pass in 100 and then 1,000. Internally, fread just multiplies those two things together and gets the total length of the file. Yeah, so somebody says, so this is basically the size of each chunk of the file, and this is how many chunks we have. So for us, the size of each chunk is 1 byte, because we're just dealing with characters, and we have the total length of the file number of entries. Okay, so first parameter is the memory chunk, the area of memory where we're going to read the file into. Then how big is each chunk of the file? How many of them are there? And then finally the file itself that we're reading from. I think it's springtime, so the pollen counts are way up, and so everyone's got these like scratchy throats these days. Okay, so we're reading into this contents chunk of memory. Each chunk of memory is 1 byte. There are st underscore size number of bytes to read in, and we're reading from the F file. Oh, let me get a drink. I hope that helped. So where did this structure come from? Somebody asked. So there's this stat structure that's defined in sys underscore stat.h. So this file contains that stat structure that I showed on the screen a little while ago. And then st underscore size is one of the fields in that stat structure. Okay, so once we read the file in, let's just go ahead and close it because we're now done with it. And I think we're going to compile the program now. And we got some errors. Oh, I see that here I misspelled error message. There we go. Oh, okay, so I see the question now. So struct stat is the name of the structure, and then st is the variable name that I'm giving it. I could have called this file info. Maybe this is a little clearer here. Okay, so the name of the variable is file info, and the type of it is struct stat. It's a 2-word type. Let me show you here. So right here, struct stat, 2-word type. And then internally, there is a variable within it called st underscore size, whose type is off underscore t. Off stands for offset in this case. So this is a variable type that can hold, I think it's a 64-bit quantity. So it means that it can hold file sizes up to whatever the maximum of a 64-bit number is. It's huge. All right, so we got it to compile. Let's go ahead and run it. And that's it. It doesn't do anything right now because we loaded the file into memory, but then we didn't do anything. Okay, so what can we do with this? So we've got our file, which now looks like this in the computer's memory. And what we want to do is make it so that we can access each one of these words or each one of these lines within the file as though this was just an array of strings. Right? I want to be able to say, go to line 3 of this file and then print out what's there, or go to line 5 of this file and print out what's there. I want to be able to do something like, say, printf %s line bracket 2, and it will go to 0, 1. It'll go to this one here, and then just print out what it sees there. So even though I've read this thing as one giant string, I want to treat it like it's a whole bunch of smaller strings. Oh, somebody pointed out that I forgot to change one more place where it said file info. So I just fixed that right here. Okay, so I'm going to erase this. I'm going to erase this for now. So here's what we're aiming towards. I've now got this file read into memory, and what I'm going to build is another array. So I'm going to have two arrays, one containing the contents of the file, and the second array that contains pointers to where each one of these words or lines within this overall file starts. So this is 0, 1, 2, 3, and 4. So now I can say, go to entry number 2, it'll follow this arrow and wind up here. Or I could say, go to entry number 4, it'll follow this arrow and go here. So this gives me instant access to any line or word within this file. So if this file contains a whole bunch of passwords, I can instantly go to any password I want to. I can go to password number 5, I can go to password number 20, I can go to password number 0, just by using this array of pointers to each one of those passwords. So this is what we're aiming towards. What we have right now is just this. Okay, so how do we get to this from here? And that's what we're going to do over the next few minutes. So the first thing to do is, well, there's many things to do here. So one of the things we need to do, and let's just kind of like build a list of things we need to do, is we need to figure out how big is this array going to be? How do we know how many entries are here? So all we've got right now is the contents of the file read into one big giant chunk of memory. How do we figure out how many individual words or how many individual lines there were in that file? Any ideas? And then the second thing we have to do is, how do we make these connections? And then also, how do we turn these individual words into strings of their own? Right now it's just one giant string. It starts here, goes all the way to here, and then there's like a new line character sitting at the end. So we got kind of three things to do. How do we figure out how big this array is going to be? How do we make these connections? And how do we turn each one of these words or lines into individual strings? So some of you already have some good ideas here. There's a suggestion, go through this array and replace all of these new lines with nulls. That's good. So if we replace all of those new lines with null characters, then essentially this is a string and it stops here. This is a string and it stops here. This is a string and it stops here. So it's just like a whole bunch of strings laid out end to end in memory. Okay, so I think we could do that. So that's one thing to do. Replace new line with null characters. How do we figure out how big this array is going to be? Remember, each one of these points to one of these words or lines within the file. How do we figure out how big this is going to be? Now, I could look at the length of the file, but that would tell me how many bytes are in the file altogether. What I want to know is how many of these individual things there are. Any ideas for that? So here we've got 1, 2, 3, 4, 5 things in here. So we want to know, how can we determine that this array should have 5 elements in it? Is there anything in the file that would tell us? Oh, there's an idea. We could basically count the number of new lines in there. Like before we went and replaced them with null characters, we could just count the number of new lines. And that would tell us how many there are. Or if we do replace them with nulls first, we could count the number of nulls. So why don't we do something like that? So let's go through the entire contents and let's replace all the new line characters with nulls. That seems easy enough. Let's just start at the beginning, go all the way to the end, and then if we encounter a new line character, go and just replace it with a null. And then once we do that, we can make another pass through the array and just count the number of nulls. Now, as I'm typing this in, does anybody see a way that we could maybe speed this up just a little bit?
Can't you combine the two loops?
How?
So after if it does find the new line character, then you just add the entries by one.
Yeah. So every time we find a new line character, we'll replace it with the null character and increment the number of entries so that we keep a count as we're going. That's really good. So we'll replace the new line with the nulls and keep count as we go. This will give us the number of entries in the file. Okay, so we're going to go through the file, replace all the new lines with null characters, and keep track of how many times we did that. And that'll tell us how many entries there are altogether. So great. We have now basically accomplished this part of it. And we now know that entries is equal to 5 for this particular example. So now we have the information to be able to create this thing here. So we know that there's going to be 5 entries in there, or there's going to be we have a variable that holds the number of entries. We're going to be using malloc to set aside space for this array because this is not something we knew at compile time. We are going to use it at runtime. So how do we calculate the number of bytes that we need to set aside? When you're using malloc, you pass it the number of bytes, but a typical way to do it is to call malloc, and then you put in something times something. where the first something is the number of elements you want, and the second number is the size of each element. So in our case, we want entries, elements, because that's how many we counted up. But then how big is each one of them? How big is each one of these things? So certainly we can use the size of function. Inside here, we're going to put what type of thing is each one of these. So let's look at the picture. What type of thing is this? It's not an integer because it points to something. So it's got to be a pointer type of some sort, but what kind of pointer is it?
Character pointer?
Good, it's a character pointer. What's it pointing to? Well, you can say, well, it's pointing to a string, but what is it actually like? What is it actually like pointing to? Well, it's pointing to this letter P. And this one here is pointing to this letter S. You see that? And this one here is pointing to the letter I. So each one of these pointers is pointing to a character. So each one of these is a character pointer. And that's what our malloc's going to look like. But there's one last piece here. We have to assign the thing that malloc returns to us to a variable. Now, let me switch back here. Now up here, where we did the malloc for the contents, what we got back was a character pointer, because this is an array of characters. So malloc is always going to give you back a pointer to something. Our goal right now is to figure out, what is this a character pointing to? What type of thing is malloc giving us back? So we're going to get back a pointer to this thing. So what is the type of this? And I'm kind of leading through this thought exercise. So each one of these is a character pointer, because each one of these points to a character. So what does this thing point to?
It points to an array of characters. So like
You're close. You're really close. All right, so this one here points to a single character. And this one points to a single character. So does this one. And so each one of these is a character pointer. This one's a character pointer. This one's a character pointer. So what does this one point to? Oh, it makes your brain hurt, doesn't it? This thing here is pointing to one of these. And one of these is a character pointer. So this thing is a pointer to a character pointer. It's a character pointer. Right? So all I did was I took whatever the type of this thing was, and I just added a star to it. That's really the recipe you need to know. So whatever one of these things is, just add a star to it. Each one of these is a character pointer, so this thing must be a character pointer. You see it now?
Didn't we do this when we were first introducing command line with the argv?
Yes.
Okay.
Yeah.
Because I was thinking that.
Right? Yeah, the other way to think about this is that this is an array of character pointers.
Okay.
Right? That's basically what it is, right? It's an array of character pointers.
I think that's what I was trying to say.
Okay. And the people on YouTube were going, it pointers, character pointers. And then finally, the light goes on. Oh, it's a pointer to a pointer. All right, so we go character, pointer. And
like
we got to
pointer inception.
Pointer inception. Then we have to give it a name. Let's call it, I can't call it entries, right? Because that's this here. Actually, now I'm thinking like maybe I should rename the variables while I get a chance. Like this is the number of entries, right? And then these are the entries themselves. All right, so now we've set aside space for that array. Now the last thing to do is to go and fill in that array with these individual characters. Now, unfortunately, we can't do that while we were counting up the entries because we didn't know how big that array was going to be. So we actually need to make two passes through that array. The first one to count the number of entries and change all the new lines to nulls, and the second pass to actually go and put those connections in. So here's what we're going to do. We know that after every null character, there's going to be the start of one of these new things. All right, so every time we see a null character, we know the very next character after that is the start of one of these entries. So as we're rolling through this array, as soon as we encounter a null character, then we'll just look at the next character, and we know that's the start of the next entry. The only place where that doesn't apply is up here at the beginning. So we'll handle that case separately. So we'll go entries sub 0 is equal to the address of contents 0. Okay, so the 0th entry points to the address of the 0th byte of the array. And now we'll do the rest. We can start at byte number 1 because we know that that's not going to be, we know we're not going to start at the 0th. And we'll go up to the file info.st_size, go up to the end of the file. And then we'll say if contents I is equal to the null character, then the next entry will be the address of the next byte. And I left these underscores here because I need a separate variable to keep track of that. So I've got I that's counting character by character through the array. And I'm going to have another variable that's counting entry by entry through the array. So I need a separate variable for that. Let's go, I don't know, E. And then I'll increment E. Okay, so we've got I that's going through this array, character by character. When it hits a null character, then we get the address of the very next character, the I plus 1th character, and then store that away in this array that's using E to count through this array. Okay, so I is counting through this one, and E is counting through this one. This outer loop is controlling the I value, and then E is being incremented within the loop because it only jumps up as we encounter each one of those null characters. Okay, so let's save this, we'll compile it, we'll run it. Now I'm not going to use it with this large binary file because it's organized. It doesn't have individual lines in it. Let's use something like, didn't I have a file that contained just a bunch of words in it? Was it hello? This one? No, that's not one. That's not an interesting one. Oh, here we go. Some text. Oh, okay, I see what's happening. So now that we have this data structure built, we should be able to just run through that data structure. We should be able to go for int I equals 0, I is less than E, which is the number of entries we have in there, I plus plus. And let's just print out each one. All right, looks pretty good. So here's our file. Pizza, sushi, fried eggs, orange juice, salmon, avocado toast, and pulled pork. And then we end up with pizza, sushi, fried egg. Looks pretty good. The only thing is we end up with this extra entry in there. This 7th entry that doesn't have anything in it. And I actually thought this might happen, and indeed it did. So what's happening there is we get all the way up to the end of this file. We find this new line, this null character sitting in the file, and then we make one more entry that points to the character beyond the end of the file. And that's not what we wanted at all. So the solution there is don't go all the way up to the end of the file. Go up one less than the end of the file, so that we stop before we hit that last null character. And now we end up with the correct number of entries. So there's a total of 7, numbered 0 through 6. Okay, so you see that again, is we went up all the way to the end of the file, and then we found that last null character and said there's one more entry following it, but there really isn't. So what we're going to get it to do is go all the way up to, but not include this very last one here. So it never sees this one, and therefore never puts one more entry into that array. I'm putting in some comments here. Connect the array of pointers to each entry in the file. All right, so all this work that we did, starting from up here, roughly line 30, or actually line 19, all this work has been done so that we can do this little loop right here on line 58 to just roll through that array of strings and then print out each one as we go. So what this allows us to do is read in a file of some unknown length and then store in an array and be able to get access to each entry in that array very quickly. So we could do it with Rocky 100. And then we end up with all of those words read in. And we can do it to the 1000 file. And we end up with all those read in. So this program, although it is fairly complex and 60 or so lines long, does a lot of work up front so that we can get very fast access to the contents of that file after all that work has been done. So whenever you're writing programs like this, there's always this trade-off between the amount of complexity of the program and then the speed up that you gain from that. When we have a data structure like this now, we'll be able to crack a whole bunch of passwords much faster because we're no longer opening the file for every single word, reading in that file, scanning through it, looking for the entry that matches, and then closing the file, and then starting the process all over again for the next one. Now that we've got all the words sitting in this array, we can just scan through that array really quickly, looking for the word that we want. Opening a file takes maybe milliseconds to do, which doesn't seem like very much time. But if you have a million of these things to crack, that could add up to actually some significant time in your program. Now we've got all the passwords read into memory, we can scan through that array really quickly, looking for the one we want. In fact, let's do something like that. That'll be the last thing we do here. I'm not going to print out each string in the file, that takes too long. But maybe I can do something now like
can you share your screen?
There we go. I could ask the user, what do you want to search for? And then we will run a loop. And then just see if the string that we're looking at is equal to the target we're searching for. Oh, now I need to include string.h because I'm doing string comparisons. So we could search for something like password. And it says it found it. Actually, I could say found it on line %d pass in I. I like that better. Found it on line 3. Let's search for Melissa. Found it on line 72. Let's search for something that's not in there. Okay, in this case, it doesn't print out that it found it, so it didn't find it. So now that we've got these passwords loaded into memory, we can search through that array really quickly without having to open the file and close it every single time we want to do it. So do you kind of see now where we can go with this? When you want to crack a whole bunch of passwords, all we have to do is just scan through that dictionary file, hash each word as we come across it, compare that to the target hash, and if it's there, we can just print out the word that we found. And if it's not there, just move on to the next one. And what we've eliminated is opening and closing the file every single time, and the time it takes to scan to that file, reading in the file one line at a time. So hopefully we've eliminated a whole bunch of overhead in cracking all these passwords, but it's still going to be kind of slowish, and there are things we could do to speed it up even more. So we're going to focus on that this coming Thursday, and then we're going to have spring break the week after that, so there'll be no sessions for the week of April 11th through the 15th, but then when we come back after spring break, we'll investigate this even more. What are some other things we could do to make it go even faster? Do you have any ideas up front here about what we could do to make this go faster? We're still going to load it into memory. Just going to load it into memory once, but what could we do to this to make it go even faster? So there's always this trade-off. Looking at a comment we got here, there's always this trade-off between speed and space. We're going to speed up the program, but at the expense of it consuming more memory. So if we have a dictionary with 1 million entries in it, we'll have to load that entire thing into memory. But once we do, we can make the program go a whole lot faster, because accessing memory is much faster than accessing the disk. So when we want to crack a whole bunch of passwords, once we've got the dictionary loaded into memory, all we have to do is scan through that array, one entry at a time, hash each one of those, compare it to the target we're trying to crack, and if they match, then we found the word. If we didn't match, move on to the next one. Hash that one, see if it matches. If it doesn't, move to the next one, hash it, see if it matches. And then once we find the match, we can just start the process all over again with the next hash that we want to crack. So one of the things that we could do to speed things up is, instead of hashing every single dictionary word every time we encounter it, why don't we do all that hashing up front? Why don't we go through the dictionary and hash all those words once and store those hashes as well? Store the dictionary word and the hash along with it. That should save a whole bunch of time, because now we don't have to hash every single dictionary word every time we want to check it. We do all that hashing up front. Store that all away. Yes, we're going to use a lot of memory to do that, but now all we have to do to crack a password is just scan through the array of hashes, and once we find that hash, there's the password sitting right next to it in memory. There's another entry, which is if you have multiple processors, split the work in two. Right? Each processor tackles half the job. Now, unfortunately, with our virtual machines, we only have one processor per virtual machine. So splitting the work amongst two processors isn't going to work. We've only got one processor, so we'll end up splitting up the job, but then one processor has to take on the work of two processors, and then it ends up being actually the same speed or slower. So that only works if you have multiple processors. Okay, so just again, a little preview as to what's to come. What we essentially have now is an array of passwords. Well, we'll call it our dictionary. And that's like 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. QWERTY, password, and so forth. And so when we want to crack a hash, we're going to scan through this dictionary, take each entry, turn it into a giant hash, and then compare that to our target. If they match, we found it. If they don't match, move to the next one. Hash it, compare it to our target. If it matches, great. If it doesn't, move to the next one. So what if we hashed this entire dictionary up front? And we turn this into a hash, turn this into a hash, turn this one to a hash, this one to a hash, and so forth. Now when we want to crack a password, here's our target. All we have to do is scan through this list and then compare each one. And when we find it, great. Let's say we're on entry number 3, then we just look at entry number 3 over here, and we know what the corresponding password is. So I think we'll do that next time. We'll do exactly that. We've already got the dictionary in memory, so we'll build another array that can hold all the hashes, and it's called a parallel array. So every entry in one array corresponds to the same entry in the other array. And then all we have to do now is scan through this array, look for the target hash. Once we find it, just look at the corresponding entry in the dictionary, and then we've got it. So this will be a great opportunity to do some timing tests. We'll time it without doing the pre-hashing, and we'll time it with doing the pre-hashing, and we'll see if there's a speed up involved there. And if there is, then we know we're making progress toward making the program faster. And then we got to start thinking about how can we make it even faster. Again, trading off space for time. More space, less time. Okay? So that's where we're going over the next few sessions. So Thursday we'll probably end up doing this parallel array thing, and then after we return from spring break, we'll start tackling the real job of making this thing super fast at the expense of more space. So this is kind of like the, I would say this particular assignment is going to be the most challenging one this semester. You remember where we started off at the beginning of the semester, where we were just making like little pictures with text? And you remember how hard that was? Well, now we're going to be building data structures and complex data structures in order to make the job of cracking these passwords faster. So we've really come a long way from just making silly little pictures out of characters. And so you should be proud, I think, of the work that you've done. And like I said, I think this will be sort of like the culmination of all the concepts. The only thing after this is computer networking. There's a few concepts to learn, but the programs will probably be comparatively much easier than this one. So I would say this one is probably the most challenging one of this semester, and we'll give you plenty of time to work on it. So it's not, this program, I think I'll end up giving you nominally about a week and a half to work on it. So we'll spend a lot of time walking you through the process. There'll be a few gaps that you need to fill in yourself, but for the most part, you'll get all of the concepts during these sessions, and then all you got to do is just put it all together. And I think it's just like the first time you run the program and it works, it's just amazing, right? Because it seems to be doing nothing for a long time as it's doing a lot of work up front, and then suddenly, boom, out comes all these passwords that are cracked, just like in a fraction of a second. It's just amazing. So the comment here, you end up hashing all these passwords, right? You build this whole parallel array. But if you're only hashing or cracking a couple of passwords, you did all that work for only a little bit of benefit, right? So let's say you've got one target hash to do. You end up hashing 1 million entries in there. You use up a lot of memory, and you only need one of them. So indeed, if you only want to crack 1 or 2 hashes, then it probably doesn't make sense to do all this work. But if you got to crack 1,000 hashes, then it might make sense to do all this work up front and gain that speed up. So again, it's always trade-offs. If you're writing a program to do one thing and then you're going to throw away the program, don't bother trying to optimize it. But if you are writing a program to do a whole bunch of work over and over and over again, you might want to spend the time optimizing it so that it works faster. Okay, well, it's just past 11 o'clock, and so I think that's about it for today. Any last questions? Well, I'll say goodbye to our Zoom folks. Hey, I hope you have a great next couple of days. Get started on this program if you haven't done it already, and come back next time and we'll do more of this group debugging thing. I really like that, putting it up on the screen and having everyone kind of look at the program and figure out what's going on. Because, you know, like I said, if you're having this problem, chances are somebody else is having a really similar problem, but they'd really like to see the process of debugging the program. So come on back on Thursday and we'll work on making the password cracking go faster. Take care. Bye-bye. And YouTube folks, same deal. Thursday, we're working on making the passwords cracking go faster. On Wednesday, in my discrete structures course, we are continuing with our graph algorithms. So we're going to be learning about probably minimal spanning tree again, maybe do shortest path, which is how your mapping applications gets you from start to finish in the shortest path possible. And then we'll have some time also probably the week after spring break to start looking at, you know, yet other graphing algorithms. So we'll spend a few sessions working on graph algorithms, and then we'll move on to the last topic of the semester, which is finite state machines and compilers and grammars and all the stuff that goes along with translating programming languages into other programming languages. Okay? Let me figure out a way to share today's code. I'll probably drop it into that Bitbucket. Let me see. Let me go ahead and do that. Where did I put that? Oh, here we go. Spring 22. What is this? Week 11? And then I'll also put in there one of these text files. All right, so git add star, git status, git push, oh, git commit -m added week 11 files. Oh, I need that password again. Okay, so that should be on the Bitbucket website. Let me bring that up for those of you who need it. So here's the address. Let me paste that into the chat here. There. Now it's something you can click on. All right. And you should be able to get into that without any password. Oh, I'm looking at the comments here. No, I think most of the people that watch on YouTube are not my students. Occasionally I get one of my students popping in. Once in a while I see one of a name scrolling by that I recognize. I'm just curious, for those of you that are still watching, I need to grab something out of my closet. Oh, actually, I moved them over here. That's why I can't find them. Have you ever used little devices like these? I have to move out of the frame. This is called an ESP32. It's a little computer. Inside of here is a little computer along with a Bluetooth and a Wi-Fi radio. So this little computer, which you can get for under $10, even cheaper in some cases, is a little tiny computer. It's got Bluetooth, Wi-Fi. I think it's got a megabyte of memory and about 4 to 8 megabytes of flash memory. And you can program it in C. And then all these little holes here along the edges you can use to attach lights and buttons and other sensors and so or displays. And so you can make a little wireless computer that can do, you know, some little job for you. So these are great little things to start experimenting with. Oh yes, and you got the Pi Zeros and you got Arduinos, which I have down here as well. What have I got in here? Again, these things are all super cheap now. These are little ARM chips. Same idea, like a little ARM processor here that has some, you know, a modest amount of memory, but certainly enough to do a small little job for you. And you've got these Raspberry Pi Picos. These are not the full-blown Raspberry Pi Linux machines, but these are very similar to these ARM boards here, where they've got, again, just like a megabyte of memory or so, a couple megabytes of flash memory, and you can hook up lights and sensors to it. These cost about $4 each. And then you can get these other ARM chips here. I have tons of these things. I just went crazy on like eBay and AliExpress. Bought a whole bunch of these things. Yeah, so these don't really have any operating system at all on them. You write the code for it, and then it's the only program that's running on these little processors. There's no operating system. There's no multi-user, you can program it to do multi-threading, but again, there's no operating system. So this one here, again, a little ARM chip, cost a few dollars. And once you load the programs onto them, you don't even have to have them connected to your computer anymore. They can run by themselves. All they need is a battery. Here are ones that I found. These are the Raspberry Pi Picos, but with an Ethernet connector on it. So I wanted to use that for a project that I was thinking about. Again, those only cost $10 each. Oh, up on the shelf, that is a Lego robot. Oh, I can't reach it right now. There's too much stuff in the way. But yeah, that's a Lego NXT robot that you can get. Those are not that cheap. But yes, you can program them. Although they really, I mean, those robots are from, like, I would say 15 plus years ago. And so by today's standards, they're really underpowered. I mean, they were a good, like, introduction to robotics and Lego at the time, but now they have, I think, their version 2 of that, which is much more contemporary. So within the last 5 years or so. And so the processor on that is much more capable, and they got much better sensors now. So we can do things like rudimentary image recognition, sound recognition, instead of just looking at light and dark and measuring distances. So I would say if you're handy at all with electronics, and there's tons of tutorials on YouTube about how to get into the Arduino programming with just little starter kits that have some lights and buttons and switches, start playing around with it. And then over time, you'll start maybe thinking about projects you could do with it. Like sometimes I have fun going to places where people are selling old toys, like old electronic toys for kids, for babies. And they'll have like buttons and lights on them, and you can open it up and basically pull the old processor unit out of it and pop one of these Arduinos in there, and maybe you can make the toy do something different that it wasn't originally designed to do. So sometimes I go to these places that sell old toys like that for $1 or $2, and just like, what could I do with this? How could I make this toy better? We got for my son those laser tag guns that you can get. They basically just shoot out, not even laser beams, they just shoot infrared beams of light out to another gun. If it records a hit, then it disables that gun for a while. Well, the cheap ones you can get on Amazon, they don't like keep score really. They just record that you got a hit, and after you've been hit like 5 times, then the game's over. But I thought it would be really cool somehow to get those things talking to each other, so you could record like who hit you and what kind of thing were you hit with. So it might disable your gun for a certain amount of time depending upon how you were hit or how close you were hit. Maybe there could be a display on the gun that would show you how many shots you have left, right? So a bunch of ways that I could open that up and maybe improve on the internals of it using one of these ARM processors. Oh yes, that book, C for Programmers with an Introduction to C11, is exactly the book that I use for this course. So So that's a good book if you are already know another programming language. So it's not intended to be like your very first programming language book. It assumes that you already have at least one other programming language, and it takes off from there. So it just shows you initially the differences between, let's say, Java and C. It assumes you already know how to do loops. It assumes you already know how to do conditionals. It just shows you the differences, and then from there, it's able to take off and do more advanced things. So yes, that's exactly the book that I use. Okay. My voice is given out, so I think we got to wrap this up. Hey, I'm glad you could join me. I will see you on Thursday. Oh, last little comment here. You discussed Valgrind with your team, and you found a lot of memory leaks. Well, I'm glad you were able to find that useful. Hopefully you're able to fix them too. All right. Well, have a great day, everyone. Tell us more about your adventures with Valgrind next time. Take care, y'all. All right, bye-bye.